Alright, so my first rework problem is number 4, the Castigliano's theorem problem, where we are asked to find the vertical deflection of a steel column standing under its own weight. And our assumptions are given as L is 25 meters, A is 0.125 meters squared, and we're also given the unit weight of steel in a kilonewton per meter cubed. So whenever I initially did this problem during the exam, my assumption for f of x was incorrect, where I did the unit weight of steel multiplied by the volume, which I found from cross-sectional area times height, which I got as this. So I multiplied those together to cancel out the meters squared to get f as this number. But that's not the full equation for f, because it needs to be in terms of gamma and a and x, because x is varying. So that was my first error. And then my second error was when taking the partial here, in the correct solution, the partial is different. So down here, the correct way to do the problem is we're given our givens here. And firstly, just to prove that gamma times a times x is a force, you can do your gamma, which is in newtons here, because I multiplied by 10 to the third. You multiply that by an area, which is in a meter squared, and you multiply that by x, which is a distance, which is just a meter. So that cancels those out, and we're just given a newton. And the partial of this with respect to f is just 1. So the partial derivative of f with respect to f is 1 when there's only one force acting on the part you're analyzing. So in this problem, our only force is the downward force due to the weight of the column. So whenever we take the derivative with respect to that force, since it's the only force, we just get 1. Next, since we have this correct f of x equation, and we have this correct partial, we can plug both of these into the axial deflection equation. So here, I firstly take out 1 over AE from the integral, since that is a constant. And then secondly, I take out gamma and A from the integral, and since those are constants. And I set my bounds as 0 to 25, because that is the full length of the column. Next, these A's actually cancel. So that gives us, with the axial deflections just being equal to gamma over E times the integral of x, which is x squared over 2, with the bounds from 0 to 25. And then plugging in 25 for x, we get 25 squared over 2 times 76.5 times 10 to the 3 to make this a newton. And then we have 207 times 10 to the 9th to make that a pascal, because we're given in gigapascals. And then whenever we multiply those together, we get our answer as 1.15 times 10 to the negative 4th meters of axial deflection. Alright, for the next set of my rework problems, I'm doing the first 2 true and false problems. First of all, I got both of them correct in terms of my answer as true or false, but my explanation for both is wrong. And so for number 1, the statement says, every possible 3D stress element can be rotated so that there are no normal stresses present. And I initially said false, because your stress tensor matrix, the normal stresses are across the middle diagonal, and I'm in linear algebra right now, and I've never seen a middle diagonal of all zeros in like a computable matrix. So this is what I used for my answer. But this is wrong. This is wrong because there's a different reason that it's false. So in a 3D stress element, there are 3 principal stresses present. Sigma 1, sigma 2, and sigma 3. Where sigma 1 is your max, sigma 2 is your middle, and sigma 3 is your minimum principal stress. But rotating a stress element to align these principal stresses will make the shear stress 0, not eliminate the normal stresses. You can rotate a stress element where only one non-zero principal stress is present. And this is the correct answer. Problem. I'm doing problem number 2, which is the second true-false problem. Here the problem statement says the optimal material on the ASPE chart comparing a material strength, SY, and density, rho, will be the material that maximizes the ratio SY to the 1/2 divided by rho. And here what I did wrong was I tried to perform some ASPE plot analysis where I set SY equal to stress, and then I solved everything in terms of the diameter, and then I got a ratio of 2 to 3, so I assumed false because my ratio in the exponent is different than what was given in the answer, so I said false. But my answer for the problem is correct, but my reasoning is incorrect. So here explains the correct reasoning. And it says, the statement is false because the slope of the ASPE plot is determined by the ratio of the exponent on the properties under comparison. However, the exponent may change depending on the geometry or the circumstance present. And what I mean by circumstance is the type of loading or the kind of the situation the part you're analyzing is in. And the exponents may change due to this geometry or circumstance, because your math up here when solving is going to be, you're going to be using different equations. You're going to be using different types of loading or forces, or a different, maybe instead of I, maybe it's J for a torque. But this is the correct reasoning.